Alright, so some simple applications of logarithms and exponentials. So the first example is in a logarithmic case. Suppose the price in dollars per unit the consumers are willing to pay for a popular high-end camera is given by that P of X. So that's price, so it's a demand function. So price is the demand, 1,450 minus 150 natural log of X, where X is in, remember, it's in thousands. So you gotta always pay attention to units. X is in thousands of units sold. And the book will do, actually this is a problem similar to one. I took one from the book and kind of changed it a little bit. So the MyLab problems, if you look at them, you gotta be wary of the units. So X is in thousands of units. And so when they give you 3,000 units, 3,000 is not the X value. 300 is the X value because X equals 300,000. So make sure you're careful. The book does this, and again, this is a problem I actually took from the book. I might have changed the numbers a little bit, but you have to be aware of this and the problems in the textbook and on MyLab. So be wary of units, and so you don't plug 300,000 in. You plug 300 in because 300 represents 300,000, and so the price at 300,000 which again, so you're plugging the 300,000 in, and I'll probably round to the penny, comes out $594.43. Alright, so that's part A. Part B, how many units will the consumers buy at a price of $300 per unit? Alright, so we want to find the X value, right? How many units when price, which is the P of X, is equal to $300. And so now they're giving you the function value. You want to solve for the X value. And so you take the function, set it equal to the value we're looking for, which is 300. And so our function is, which is why we practice how to solve these, right? So first thing, isolate the natural log. So subtract that. 1,450. I keep trying to miss the 4. And so I get negative 150 natural log of X equals negative 1,150 divided by my negative 150. Negative 150. And again, I'm going to go over here. And so I've got the natural log on one side, right? So once I have divided out that negative 150, all I'm left with is the natural log over here. Again, don't round, leave it as X. So you can leave it if you wanted to. You could leave it that fraction, or you could reduce it, which I'd probably reduce it, but that's because that's the math person in me. You could leave it the first fraction. So I've got the natural log of X equals 23 over 3, but don't round because you'll get significantly off, because remember, my next step is to raise both sides to the E. So over here I'm left with X, over here I'm E raised to the 23 over 3, if I can write that correctly. 23 over 3, which then you use your calculator. It comes out, again, I'm just going to round to the whole number, which, remember, that means 1,000. So they can sell, this is 1,000. So I'd probably write it cameras. Or you can use the word 1,000, 2,123,000, which is 2,123,000 units. Right, in that example. Now the second one. So the last one for this set of notes. So we've got Americans are paying for organic product, right? A of T is in billions, so remember, it's in billions of dollars spent on food 2 years after 2014. So what that means is 2014 is times 0, which means 2015 would be 1 year later, and so on. Right? A, estimate the amount that Americans spent on organic food in 2017. So A would be 2017, which would be 3 years after 2014. So the T value, I don't plug in 2017. I plug in 3 years after 2014. And so I'm going to find A of 3. So again, be careful with units in this chapter. All right, that comes out to 48.91. Remember, it's in billions of dollars spent on organic food. All right, so almost $49 billion spent on organic food, 2017. All right, when will the amount the Americans spend on organic food exceed 50 billion? All right, so when will, which means we're looking for a time, our A of t, and we want to be greater than 50, but in order to find the greater than 50, what we're going to do is we're going to say equal to 50. Oops, my phone is going off. Sorry about that. So A of t is equal to 50 is what we're going to solve for, and we just want to be bigger than that time value. So our t is going to be greater than whatever that time value comes out to be. All right, so I'm going to take my 335.8 e raised to the 0.104t, set it equal to 50, and solve for t, which is why we practice solving equations, because we'll be using them in applications. All right, so first step, isolate the e, so divide by that number. Again, do not round. So either leave it exactly that or write the reduced fraction. I'm just going to leave it this time. Sometimes in applications, it's just easier to leave it. If you want to write the fraction, hit the reduced fraction key on your calculator, you can. You're going to take the natural log of both sides. So on this side, the natural log cancels with that e, and so I'm left with the 0.0104t equals the natural log of that fraction. All right, that fraction is inside the natural log, and then the last step would be divide by that number in front of the t. And so t comes out to be whatever the natural log of 50 divided by 35.8, then that expression, so once I do the natural log of that, so that goes in the natural log, divide that whole natural log, right, the whole natural log gets divided by that 0.104, and it comes out 3.212, which means, remember, when it exceed 50, so 3 was 2017, to exceed that, we'll go by 2018 will exceed 50 billion. All right, so again, sometime within 2017, they'll hit 50 billion. And so by the next year, they'll exceed that. They'll be over the 50 billion. I believe there's one more part to this. When will the amount Americans spend on organic food double? All right, there's a couple ways you can do this. All right, depending on how comfortable you are and what you remember about these. So part C, there's two ways you can figure out when it will double. So we want to find the time, the t. The amount from 2014 will double. All right, so first of all, what you have to do is figure out, well, how much were they spending in 2014? Well, 2014 was times 0. So A of 0 was my 35.8 e raised to the 0. And so it's that number out front. That number out front is my original amount. So they were spending 35.8 billion. I'm going to write million instead of billion. Billion. By 2014. And so we want that to double. Alright, and there is, and again, the book kind of goes through the doubling time. You could use, there's a little trick equation, and I'm going to talk about that at the end. So you know the little trick, you can go ahead and use it. But if you don't know the trick, alright, this would be the process you use to solve. Alright, and so I want it to double. So at what time will my A of t be twice that 35.8 billion? So when will A of t equal, well, 35.8 times 2 is 71.6 billion. All right, so when will the amount Americans spend on organic food reach 71.6 billion? And so now you just set your equation equal to that and solve. So you take your 71.6, set it equal to your 35.8 e raised to the 0.104 times time, and then solve that, right, using the same methods we used before. Again, I'm just going to leave that exactly that fraction, not changing it. natural log. So I've got the natural log of that ugly fraction, which again, if you want to reduce it but leave it exact, you can do that on your own. And then last step, divide by that number in the exponent. Alright, so t comes out to be 6.67 if I round 2 decimal places. Just go around 1 decimal place, so 6.7. Alright, which would be years after 2014. So almost in 2020. Alright, towards the end of 2020. That's one way. Alright, so again, that's one way you could solve it. There is a little trick that's called the doubling time formula. Alright, so if we've got an equation where, again, in this case, we've got our a of t equals the number up front, the original amount, b raised to some number k times time. Right? That's just sort of the generic version. If I want to know when it will double, alright, well, the time it takes to double is the natural log of 2 divided by whatever that k value is in front. And so our function was 35.8 e raised to the 0.104 times t. And you'll check to see that this is true. T equals the natural log of 2 divided by the point, and it will come out to the same value we got before, 6.7. Alright, because if I did reduce this, which I didn't up here because I knew I was going to get to there in a second, if you take your 71.6 and divide it by your 35, it does reduce to 2. Alright, so it does give you that expression, natural log of 2 divided by, and that will always happen when you're looking for double time. And so if you know this little trick, you can use it if they ask for double time. If you don't remember this little trick for doubling time, again, it's not that hard to figure out how long it doubles. You just take whatever your original amount was, double it, and then solve using the same methods we used previously for finding any value. But this little trick just works for doubling time, so only use this when we're looking for a doubling time. Alright, we'll stop there. That finishes up sort of a quick and dirty review of exponentials, logarithms, solving equations, and looking at some basic applications. We'll get into the calculus of it in the next 2 sections. 2.2 and 2.3.